Hello, everyone. Welcome to our channel once again, Making Life Easier. And welcome once again to our series on basic mechanics, And today we are looking at moment of a force about a point, example 2. Moment of a force about a point, example 2. Quickly, let's look at our question and how to solve it. Good. Two cables, PM and QM, are used to hold a large block from falling. If the tension in the cables, PM and QM, are 700 newtons and 550 newtons respectively, determine the moment about O of the resultant force of the cables exerted at M. The resultant force of the cables exerted at M. So let us look at how to solve this problem. We have been given this and we are told that this log is being kept in this position by two cables, which is PM and QM. And we are asked to find the moment of the resultant force exerted at M. So how do we solve this problem? How do we solve this kind of problem? Good. So first of all, we know that moment of a force. Take note that in this case, you can see that our diagram is three-dimensional. Our diagram is a three-dimensional object. And so I advise that anytime you are given a three-dimensional object, do not use the scalar approach. Rather, I would prefer you use the vector approach. And you have already seen that the vector approach is always R cross F. Take note of this formula. It is not equal to, the formula is always R cross F, not F cross R, not this one, not F cross R. It's rather R cross F. This is our formula for finding the moment of a force using the vector approach. Good. So now let's consider the cables one after the other. So from here, we can draw our free body diagram. And don't forget that the question says that the moment of the resultant force of the cables exerted at M. So it means that in this question, our point of interest is M. Our point of interest is M. And for cables, anytime you are dealing with cables, it always points away from your point of interest. And here, because the question says that the resultant of the forces exerted at M, the moment of the about O, the resultant of the forces exerted at M, it means that our point of interest is M. So our cables will point away from our M. Our cables will point away from M. To point away from M. Good. So now let's consider the cables one after the other. Let's first of all look at cable PM. Cable PM. Good. So cable PM or empty, let's rather prefer and write it as empty because our focus is at point M. So our force will be moving from M to P. Good. So from here we can say that moment one or moment for cable MP will be equal to, we are taking our moment at O. So our R M/O times our force, our tensional force in MP. Our tensional force in MP. So first of all, let's find our R M slash O. And we have already explained that this is called the position vector. This is called the position vector. And what does it do? It indicates the position of where the force is applied, where we are taking our moment. That is why you can see that we have written the formula as R M slash O. So always you are going to move from where you are taking your moment to where the force has been applied. You move from where you are taking your moment to where the force is applied, but not where the force is applied to where you are taking your moment. Be careful with that. So it means that here we are moving to M when we are starting from O, where we are taking our moment. So from here, we can say that if we are at O and then we want to move to M, we will just move on the vertical like this and then we will get to M. And you can see, don't forget that we said that our unit vector conversions are this. And anytime we are moving up on the Y, it's positive. Anytime we are moving on this, on X, it's positive. And anytime we are going this direction on Z, it is positive. So this is positive, this is positive. When we are moving in the opposite direction, then this is negative, and this is also negative. Good. So now you can see that when we are moving from O to M, we'll be moving up. And from our conversion, when we are moving up, it's positive. So we are going to get 10 to be positive 10, but it's in the y-axis. So we represent it with J. Good. Once we are done with that, then we are left with our force here, So we can say that our force in the vector form is always equal to our scalar force times lambda. And here, this lambda is once again referred to as the direction cosine. The direction cosine, because it indicates the direction of the force. And I've told you that our force MP will be moving from our point of interest M to point P. So we'll be moving from M to point P. So if we are moving from M and then we want to get to P, then what distances are we going to move? First of all, let us write our formula for lambda. Since in this question we are not given angles, we have been given distances. So we can say that our lambda will be equal to from the vector from M to P. So vector MT over the magnitude of vector MT. That will be our lambda. And this is equal to the xi over plus the yj plus the zk all over k. So from here, we first of all need to find MP, vector MP, which means that if we are moving from our point of interest where the force is applied at M to P, which direction are we going to take? So it means that from M to P, we are going to move vertically like that. But now you see that we are moving downwards. So it's going to be negative on Y. So on Y, we are going to get negative 10J. And then we move this distance on the Z. You see it's in the same direction with our Z. So we move this distance on Z. So that is going to be positive. So we are going to get on the Z, we are going to get positive 5K. And then from there, you can see that on this line, we need to move to this point on our X. We need to move from this to that before we can get to point P. We have to move from this to that before we can get to point P. And we are told that the distance from this to that is 0.5 meters. And look at our X is moving this direction. But now we are moving from this point to that point. So it means that our X is also going to be negative. So our S is going to be negative 0.5 I. Then once you have gotten this, the next step is to find the magnitude of MP. So magnitude of MP will be equal to the square root of negative 0.5 square plus negative 10 square plus 5 square. Good. And from here, we can get the magnitude of MP to be 11.2 meters. 11.2 meters. So from here we can get our lambda. So our lambda will be equal to our MP vector all over magnitude of MP. And from here we can say that our lambda will be equal to negative 0.5I minus 10J plus 5K all over the magnitude, which is 11.2. So from here, our lambda, which is our direction cosine, is going to be negative 0.045I minus 0.893J plus 0.446K. And once you have gotten our lambda, now we can get our F, because we know that our F will be equal to F lambda. So this is our force in the vector form. This is our force in the vector form will be equal to the scalar force times lambda. So our force in the vector form therefore will be equal to, we are told that the force in EM or MG is 700. So this is going to be 700 times lambda, which is negative 0.045 I minus 0.893 J plus 0.446 K. Then from here, our F in the vector form is going to be negative 31.5 I minus 625.1 J plus 312.2 P. So we have gotten our force in the vector form. So now we can determine our moment, isn't it? So our moment one, we said that is RMO cross F in the vector form. So from here we can say that our moment one will be equal to NJ cross our force, which is negative 31.5 I minus 625.1 J plus 312.2 K. And from here, we said that the best way to solve this is to put it in the matrix form. So we have I, J, K. And this is our position vector. We only have the J component. So we have 10 here. And the rest will be 0, 0. And then write the component for our force, which is negative 31.5, negative 625.1. And then on the K, we have 312.2 K. Then we can use the method of determinants to find our I component. Don't forget our J component and our K component. Don't forget that this is plus, minus, plus, plus, minus, plus. So from here, we are going to, we said that if you want to get the I component here, you take away all this, and you'll be left with a 2 by 2 matrix. So this times that, and then this times that. So we are going to get for I component, we are going to get n times 312.2 minus 0 times negative 625.1, and this will be our I component. And then for our J component, we take away everything which is J, but don't forget this minus. So this minus is what we have written here. And we take away all the Y component or all the J component, and we left with the S component and the K component, and we find the determinant. So this times that minus this times that. So we are going to get 0 times 312.2 minus 0 times negative 31.5 J plus. And now we want to get our K component. So we take away everything for the K. We cross all the K's out and we left with this. So it will be this times that minus this times that. So we are going to get negative 625.1 times 0 minus negative 81.5 times 10. And all this will give us our K components. And then from here, we can easily get our answer as 3122I plus 315K. Good. So this will be our moment for cable MT. What will be our moment for cable QM? Quickly, let's run through that also and see our moment for cable QM. And see our moment for cable QM. So for cable QM also, we are going to, it is going to be R cross F. And we have stated that our F should be in the vector form, and our R, which is the position vector, should also be in the vector form. So let's look at how to solve for that of QM quickly. Good. So for QM also, first of all, for QM also, first of all, we need to, so for cable QM, for cable QM. So our moment, as we said, is going to be, so this, let's take that this one is moment 2. It's going to be R. So we want to get to M when we are standing at O. Don't forget that our focus was the resultant force at M, the moment of the resultant force at M, right? So our interest is at M. So we want to move from O to M. So we are going to get RM/O cross our force for MP, or our force for QM, our force for QM or MQ. So from here, our RMO, we said that we'll be moving from point O to where the M is. So it means that we are going to move vertically to that point, and we are moving up. We are moving up from O to M. So we said that it's going to be positive 10J again. And now let's determine our force, our FMQ in the vector form. In the vector form is going to be F lambda. So the first thing we need to do is to determine our lambda. And we said that lambda will be equal to, so in this case, we have MQ, vector MQ, over the magnitude of vector MQ. And we said that this is the same as distance in the x-axis plus distance in the y plus distance in the z, all over b, all over b. Good. So from here, we can determine our lambda. So our lambda, we want to move from the point M, which is our focus, to where the force is ending. So you can see that here, our focus is on point M, and we said that the force always points away from our point of interest. So we are going to move from M till we get to the point L. So we are saying that here we move this distance on the y, but see, we are coming down. So our y component is going to be negative. So our y component is going to be negative NJ. And then from this point, we move on the x, this distance. We move on the x, this distance. Sorry, let me indicate it where we move on the x, this distance. Good. We will move this distance on the x. So we said that we are going to move vertically this distance on the y, which is negative 10 because we are coming down. And then we move this distance on the x, but this distance is in the same direction with our x. So that distance is going to be positive 4i, positive 4i. And then from here, you can see that we have to move 1 meter before, we have to move 1 meter. If you can see, we have to move 1 meter before, from this point, we need to move 1 meter before we can get to this point. And this direction is in the Z. This direction is in the Z, but it's in the same direction with our Z. So from this point, you move to this point. Therefore, we are going to get positive 1K. Positive 1K. Then once you have been able to do that, don't forget, this one is not lambda. This one is MQ. This one is MQ, vector MQ. So once you have gotten our vector MQ, the next thing is to get the magnitude of MQ. The magnitude of MQ. And the magnitude of MQ is going to be the square root of 4 square plus negative 10 square, which will be positive, and this will be 1 square. And from here, our answer is going to be 10.8. Once you have gotten this, we can determine our lambda. Our lambda will therefore be equal to 4I minus 10J plus 1K all over 10.8. And from here, our lambda will be equal to 0.37I minus 0.93J plus 0.09K. Then from here, we can determine our F. We said that F is equal to F in the vector form is always equal to F in the scalar form times lambda. And we have been given F in the scalar form as 550. Therefore, we are going to get 550 into brackets our lambda, which is 0.37I minus 0.93G plus 0.09P. Then from here, we can get our force as, 203.5 in the x-axis, I, and then we'll get on the y-axis, it's still negative, so negative 511.5G, and then on the z, we have 49.5K. And once you have been able to do this, the next thing, we have our force in the vector form. We have our position vector. So we can find our moment. Our moment to be equal to RMO cross our force in the vector form. And from here, we just write them together. So again, we have 10G cross our force, which is 203.5I minus 511.5G plus 49.5K. So from here, we just drew. We said that the easiest way to do it is to use a matrix method. So we have I, J, K, and we said that this is plus, minus, plus. And we write for the position vector, we only have 10. This is 0, this is 0. And for the force, this will be 203.5. This will be negative 511.5, and the last one will be 49.5K. Then we can determine we can be able to determine the determinant from the matrix method. So we said that if you want to get a determinant, for I, you cross all the I's and you'll be left with the 2. So it means that we are going to get this times this minus this times that. Very simple. So we are going to get, for I, we are going to get 49.5 times 10 minus negative 511.5 times 0. And everything there will give us our I component plus. For the Y component, don't forget that the negative is there. So this is going to be minus into bracket 0 times 49.5 minus 0 times 203.5, and all this will be the J component. And for our Z component, we are going to get 0 times negative 511.5. Because our Z component, we take away all the Z components, and it will be this times this times this, minus this times that, minus this times that. So you are going to get this minus 10 times 203.54 P. And from there, we have our moment as 495 I minus 2035 P. And because it's a moment, the unit is Newton meter. And then from here, we have gotten our moment. This is the moment for F1. So this is the moment for F2. So this is M2, or the moment for Qm. And we had already determined the moment for M1, which was for MP. And we got M1 was 3122 I plus 315 K. This was our M2. So it means that here we have two moments. So if you want to get the resultant, we just put them together. So our resultant moment is going to be M1 plus M2. And from here, we just add all the I components, we add all the K components. So our answer is going to be 3, 6. If you put this and that together for I, and you put this together and that for K. So you are going to get 3617 I minus 1720 K. And then we have gotten our resultant moment at M. So that was pretty simple, just that it requires a lot of calculations, but I'm sure we have understood clearly. If you have any question, any suggestion, or any comments, you can leave it at the comment section, and we will appreciate that. Kindly subscribe, and once again, thank you very much for watching, and we'll be happy to assist you if you have any challenge regarding this. Once again, thank you for watching. Kindly subscribe to our channel and hit the notification bell as well. See you, bye-bye, in our next video.